So is a worn shaft journal suddenly the biggest headache keeping your critical machinery running?
Yeah, it happens, right?
You know the drill.
Hmm.
Unplanned downtime hits hard, and those repair bills can be absolutely brutal.
They really can.
But what if there's a way to sidestep that whole, weeks-long ordeal of fixing these really vital
Well,
parts?
that's what we're going to dive into today. We're looking at portable shaft turning machines.
Okay.
Think of it like bringing a precision machine shop right to your ailing equipment.
Right to the site.
Exactly. And the core win here, it's dramatically less downtime. Why? Because you completely skip the hassle of removing the shaft,
Yeah.
shipping it out, all that stuff.
Oh, absolutely. I mean, picture the traditional way.
Yeah.
It's days, maybe even weeks,
Hmm.
right? Taking everything apart, wrestling that huge shaft out, if you can even get it out sometimes.
And the cost of just transporting it,
Right.
specialized trucks, permits.
Yeah, specialized costly transport to some workshop miles away, then you wait.
You wait in line at the shop.
And then the whole intricate puzzle of putting it all back together again. Ugh,
It's enough to make you want to just, ignore the problem, which we all know is, well, it's a recipe for disaster later.
totally.
And that's precisely where these mobile marvels come in. Our goal today in this deep dive is to really get our heads around how this tech gives you a much faster, way more efficient path to getting that essential machinery back online.
Okay.
Now look, there are other ways to deal with shaft damage, obviously, but we're focusing today specifically on the machines that fix the shaft itself, right there.
Gotcha. Okay, so let's get down to brass tacks.
Mm.
What exactly does a shaft turning machine do? I mean, we're talking about some seriously heavy components inside some pretty big machines.
Yeah, good question. In essence, it's basically a portable, specialized lathe.
Okay, a lathe, but portable.
Right. But here's the twist. Unlike a traditional lathe where the shaft itself spins,
Yep.
here the machine clamps onto the stationary shaft. The shaft stays put. Then it uses cutting tools that rotate around the shaft to precisely shave away the damaged material.
So machines it in place.
Exactly. It brings the shaft back to its correct dimensions, gets the surface finish right, all without moving it.
So we're really talking about situations where pulling those shafts out is just, maybe buried deep inside some huge piece of equipment.
Precisely,
Yeah.
where removal would be outrageously expensive or maybe just physically impossible.
That sounds like a fundamental shift then. You're taking that fine-tuned machining capability straight to where the problem is.
Absolutely. It's almost like turning the whole concept of a regular lathe, inside out.
Right. The tool moves, not the workpiece.
Exactly. The workpiece, the shaft, is fixed, and the tool does all the rotating around it. Now, the process itself involves a few key steps. First off, there's the mounting.
How does it attach?
Well, these machines use really strong clamping systems. Often it's a 4-jaw chuck, sometimes even 8 adjustable jaws.
Okay, like on a regular lathe check.
Sort of, yeah, but designed to grab onto the shaft's outer surface securely. This gives you that absolutely critical, stable, centered foundation to work from.
Makes sense. You need it rigid.
Totally. And the design really focuses on making the setup and the adjustments quick and, relatively easy. That's a huge plus when you're out in the field, maybe in an awkward spot.
Yeah, you definitely don't want to spend half your day just trying to get the thing bolted on straight.
Okay.
Okay, so it's mounted securely. What's next?
Okay, next up is the rotating body. This is the main chunk of the machine, you could say.
Right.
It holds the cutting tools, and it also holds the motor, the drive system that powers everything.
And this whole thing spins.
This whole unit rotates smoothly around the shaft that you're working on.
Okay, and the cutters.
The cutting tools themselves are pretty standard, actually. Similar to what you'd find on a regular workshop lathe, they're mounted on adjustable tool posts, which are attached to that rotating body.
Gotcha. So how do you control how much material you're taking off and where?
Ah, that's the feed system. It's crucial for precision. It carefully controls 2 types of movement.
Okay.
There's axial feed, which moves the cutter along the length of the shaft.
Yeah, like turning down a diameter.
Exactly. And then there's radial feed, which moves the cutting tool in or out, towards or away from the shaft center.
Ah, okay, so that sets the depth of cut.
Precisely. And these accurate feed systems let you do both roughing, taking off a lot of damaged material quickly to get down to good metal, and then those super fine finishing passes to get that perfect final surface.
Okay, so it really is mimicking the actions of a standard lathe.
Yeah.
Just configured differently. What's actually driving it? What provides the power?
The drive system. It's typically either electric or hydraulic motors.
Powerful ones, I assume.
Oh yeah. The better machines have significant horsepower. And, really importantly, They often have what's called stepless speed regulation, meaning you can fine-tune the rotational speed precisely, dialing it in for the specific material and cut. And crucially, it maintains constant torque, that twisting force, across a wide range of speeds.
Why is that so important?
Well, that consistent cutting action, that steady power, is absolutely vital for achieving high accuracy and a really smooth surface finish. You don't want the cutter bogging down or speeding up mid-cut.
Makes sense. And you mentioned getting workshop-level precision, but on-site. How do they manage that? Seems tough with a portable unit.
It is, but it comes down to some serious precision engineering built right in. First, they need to be incredibly rigid. The frame has to minimize any vibration.
Right. Vibration's the enemy of precision machining.
Exactly. Even tiny vibrations can mess up a precise cut, especially on the finishing pass. They also use really high-quality components. Things like heavy-duty guideposts and guide sleeves act like very precise rails, keeping everything perfectly aligned and stable during the cut.
So good bearings, good guides.
Absolutely. Reliable bearings are essential too for smooth rotation, stability, and just the machine's overall durability. And another clever thing is often they have a modular design.
How does that help?
Well, it makes them adaptable. You can often break them down slightly or configure them differently to fit into really tight spots or work around obstructions near the shaft. It adds a lot of flexibility in the field.
That's smart.
Yeah.
And materials. What can they typically handle?
Oh, the common stuff you find in heavy machinery. Steel, alloy steels, copper, stainless steel. They're built to cut these materials effectively.
Okay, so it sounds like it's more than just fixing, say, a worn spot where a bearing sits. It sounds quite versatile.
Exactly right. It's definitely not a one-trick pony. While worn bearing journals or seal surfaces are probably the most common jobs, its usefulness goes way beyond that.
Like what else?
Well, these machines can tackle various kinds of damage, obviously where from friction, contamination, maybe metal fatigue, but they can also correct minor bends in a shaft and repair damaged keyways, those slots for keys that lock gears on.
Yeah, crucial for transmitting torque.
Right. Or repair damaged threads. Plus, they can accurately machine the outer diameters, cut critical grooves for seals.
Like O-rings.
Exactly. O-rings, hydraulic seals, things like that. They can even cut V-grooves and create chamfers, those angled edges you often need.
Okay, let's talk about wear for a second. You mentioned different types.
Yeah, when we talk about wear repair, there are a few common culprits you see out there. There's adhesive wear.
What's that?
That's basically when two metal surfaces rub directly, metal on metal, often because the lubrication breaks down under heavy load or at certain speeds. Bits can kind of weld together and then tear off.
Ouch. Okay.
Then you've got abrasive wear. That's caused by hard particles, think dirt, grit, maybe little bits of metal floating around in the lubricant, getting between the moving parts.
It's like sandpaper, basically.
Exactly like sandpaper.
Yeah.
Grinds things away. And finally, there's fatigue wear. This comes from repeated stress cycles over a long time. Poor lubrication can definitely make it worse, accelerating the fatigue.
So how does the machine fix these? Just grinds it smooth?
Well, it machines it smooth and true.
Yeah.
It tackles these by machining the worn area down past the damage to a clean, uniform diameter. It restores the shaft's original geometry, its roundness and concentricity.
And then is it the right size? Or is it undersized?
Often, it'll be slightly undersized after cleaning up the wear. So this machining step creates an ideal surface for then, say, fitting a repair sleeve over the top.
Oh, okay.
Or for building the diameter back up using welding or perhaps metal spring techniques. Then you'd typically do a final machining pass with the same machine to bring it back to the precise original dimension required.
Got it. That makes perfect sense. What about the other damage types you mentioned? Bending.
Right, bending repair. Now, it's important to stress this is for minor bends.
Not like if a truck ran over it.
Huh. No, definitely not. If a shaft is severely bent or warped, it almost certainly needs replacement. But for those slight deviations, maybe caused by long-term stress or a minor impact, the machine can essentially remachine the shaft surface so it's perfectly true to its actual center of rotation.
So it corrects the runout.
Exactly. It effectively straightens the functional surface within acceptable limits, even if the core of the shaft still has a tiny bit of bend. And keyways. Damaged keyways, maybe the edges are rolled over or widened.
Yeah, or threads that are stripped or dinged up.
Yep, those can often be cleaned up nicely. Or, in some cases, completely recut using specialized tooling on the machine, restoring their proper function and accuracy.
Hey, grooves. You mentioned cutting grooves.
Yes, groove cutting. The machine can precisely create new sealing grooves where needed, maybe for O-rings or hydraulic seals, or repair existing ones that have gotten damaged.
V-grooves, too.
V-shaped grooves as well, yep. And of course, just straight outer diameter machining is a primary function, creating or restoring those super precise cylindrical surfaces needed for bearings, journals, seals.
Even on really big shafts.
Especially useful on large diameter shafts where other methods are impractical. And lastly, chamfering or angled cuts, because the tool holder can often be swiveled, usually up to 45 degrees. The machine can create those angled chamfers on shaft ends or shoulders, or machine other specific angled features if required.
And the precision level, what are we talking about?
It's actually quite impressive for a field machine. For roughing, you can take fairly deep cuts, maybe up to 5 millimeters, to remove material efficiently.
That's quite a bite.
It is. But then for the finishing passes, which are critical for performance, the surface roughness can typically be brought down to around raw 3.2 micrometers.
How smooth is that in real terms?
Well, it's smoother than most finely sanded wood. It's a good functional finish suitable for many bearing and seal applications. The whole goal, remember, is restoring those critical dimensions and the surface quality for reliable performance.
All on site.
All done on site without ever pulling the shaft.
Wow. Okay, this sounds like an absolute lifesaver, as you said, for a lot of heavy-duty industries. Which sectors are really finding this technology indispensable?
Oh, you're spot on. It's a total game changer, especially for industries dealing with really big, critical machinery where the shafts are just incredibly difficult or time-consuming or sometimes practically impossible to get out.
Like who?
We're talking sectors like steel mills, definitely paper mills, power generation that includes hydro, thermal, and increasingly wind power,
Turbines, yeah.
shipbuilding and repair, mining and heavy machinery, even things like aerospace and certain applications, oil and gas, and rubber and plastics manufacturing.
That's a broad range.
It is. Basically, any industry that relies heavily on these large, essential shafts that are just a complete nightmare to move.
So what's the common factor? Just the size and difficulty of removal.
That's the main driver, yeah. The immense challenge and the sheer cost associated with removing, transporting, and reinstalling these massive components. Let's take iron and steel metallurgy.
Okay.
Think about rolling mill rolls, the work rolls, support rolls, drive shafts. These things are enormous under incredible stress, and they run pretty much nonstop.
Downtime is killer there.
Exactly. Trying to take one of those behemoths out, huge disassembly costs, specialized cranes, and incredibly long periods of lost production. It's just not feasible sometimes.
Right, paper mills.
In the paper industry, you've got things like calendar rolls, dryer rolls, press rolls, guide rolls. These often have very, very long
I've
shafts.
seen pictures, they're huge.
Yeah. And they need to maintain perfect roundness, high concentricity, and their surfaces need regular repair because of the constant contact with the paper pulp or the finished paper. Again, pulling them out is a major undertaking.
Power generation. You mentioned turbines.
Right, power generation. Think about massive turbine shafts in hydroelectric plants or steam and gas turbines in thermal plants. Generator rotors, too. And as we mentioned, the main shafts in wind turbines.
High-value assets.
Incredibly high value. Any downtime there translates directly into massive financial losses from lost power generation. And specifically with wind turbines, doing the repair on site, up tower,
Yeah.
avoids that unbelievably complex and expensive process of bringing in huge cranes to take the nacelle apart, lower components. It's a whole different ballgame doing it in place.
Wow, yeah, I hadn't fully grasped the logistics of fixing a wind turbine shaft way up there. That's incredible.
It really is. Then you've got shipbuilding and repair,
Yeah.
propeller shafts, propulsion drive shafts, rudder stocks.
Long and heavy.
Incredibly long, incredibly heavy, often running right through the ship, getting them out within the tight confines of a ship's hull or during a limited dry dock period. Major, major costly operation.
Makes sense. Mining.
Mining and heavy machinery. Think giant excavators, haul trucks, hoist drums on mine winders, winch shafts, crane components. This equipment operates under extreme loads, often in really remote, dusty, harsh locations.
Right, far from workshops.
Exactly. Leads to significant wear on their heavy-duty drive shafts. And the machines themselves are just physically enormous. Transporting parts is a huge hurdle.
Okay. Rubber and plastics. What's the issue there?
The rubber and plastics machinery industries use things like cooling rolls, heating rolls, mixing shafts, traction shafts. These often need very precise surface finishes.
For product quality.
Yeah, and for heat transfer or material handling, they often require regular refurbishment because the processes themselves can be demanding on the surfaces. On-site repair keeps them running efficiently.
Oil and gas. Remote locations again.
Oil and gas, definitely. Pump shafts, compressor shafts, components and drilling equipment, often located in very remote areas or hazardous environments like offshore platforms.
Where moving heavy gear is tricky and risky.
Extremely complex and risky, yeah. And finally, even aerospace. You might not immediately think of huge shafts there,
Not typically, no.
but they use them in large assembly fixtures, big component testing rigs, ground support equipment, things used to build or maintain those large, high-precision aircraft parts. Being able to maintain these fixtures on site avoids incredibly complex logistics.
So across the board, really.
Pretty much. Across all these industries, bringing the machine tool directly to the problem saves just a tremendous amount of time and money compared to that traditional off-site repair route.
Yeah, it's really clear now why these industries are so reliant on this. So just to really nail down the core value here, what are the main reasons, summarizing, why a shaft turning machine is just so well suited for these tough field machining jobs?
Okay, yeah, boiling it down, the key advantages are really about, 1, massive savings in both time and cost, 2, a significant improvement in safety, 3, the ability to perform highly accurate, customized repairs right there, and 4, just a dramatic reduction in how long that critical piece of machinery is out of service. When you can get that precision machining done right where the shaft lives, the benefits are truly significant, especially, like we've said, when you're dealing with those incredibly large or deeply integrated machine parts.
Okay, let's just unpack those advantages a little bit more. Time and cost savings, you're saying that's often the biggest driver?
Oh, absolutely. It's usually the #1 reason people look into this. By completely eliminating the need to disassemble everything around the shaft, take the shaft itself out, arrange that specialized transport,
The shop wait time?
wait for an opening in a machine shop schedule, pay their rates, and then go through the whole complex process of putting everything back together again. You're potentially saving days, maybe even weeks of downtime,
Condensing it down how much?
often condensing it into just hours or maybe a few days of actual work right there on site.
That must translate into huge cost savings.
Directly. Huge reductions in repair costs, labor, transport shop fees. I mean, I've personally seen repairs completed during short planned maintenance shutdowns that would have been absolutely impossible schedule-wise if we had to send the shaft out.
And less downtime means?
Less repair time means the equipment is back making money much faster. It directly boosts the plant's overall efficiency, its profitability. It's huge.
And safety. You mentioned improved safety.
Yeah, that's a really important aspect, too. Think about it. Avoiding the need to disassemble, rig, lift, and transport those incredibly heavy, awkward shafts.
Lots of potential hazards there.
Absolutely. It significantly reduces the risks for the maintenance crews involved, and it also lowers the potential for accidental damage to other expensive parts of the machinery during removal or reinstallation.
Good point. And the repairs themselves, you said customized and precise.
Right. These portable machines, they can be configured very specifically to the exact conditions of the job site and the precise type of repair that's needed. And despite being portable, remember, they're built with that inherent rigidity. They use those precision guide systems and carefully controlled feed mechanisms. All that ensures that the repaired shaft meets the strict geometric tolerances, the roundness, the straightness, and achieves the necessary surface finish for optimal performance.
So you're not sacrificing quality by doing it on site.
Not at all. If you have the right machine and skilled operators, then there's the adaptability and accessibility we touched on the modular designs.
Right, for tight spaces.
Exactly. They can often be maneuvered and set up in tight or awkward spaces where getting traditional machine access would just be impossible. And the fact that they clamp directly onto the shaft surface often helps overcome logistical problems caused by, say, gears or couplings blocking the shaft ends.
Ah, good point.
Yeah.
Don't need access to the end necessarily.
Often not, no.
No.
And finally, just to reiterate the powerful capability, it's vital to remember that even though they're portable, these aren't lightweight tools. They're engineered to deliver significant power for efficiently removing material during those roughing cuts. And they provide the stability needed for those super precise finishing passes. Ultimately, they deliver results that are genuinely on par with what you'd expect from a well-equipped, stationary machine shop,
but without leaving the job site.
all without leaving the job site.
So it really is about bringing the solution right to the problem, isn't it? Instead of trying to wrestle the problem halfway across the country to a solution.
Precisely. It just provides a faster, much safer, more economical, and highly effective way to handle some of the most challenging maintenance situations you can possibly encounter in industry.
Well, there you have it. On-site shaft turning machines seems like a really quick, accurate way to repair those worn shaft journals and, well, other kinds of damage too, without all the cost and time involved in removal.
Yeah, they save that crucial time, they definitely cut down on expenses, significantly improve safety for the maintenance teams.
And just play a vital role, it sounds like, in keeping essential heavy machinery up and running across just a huge array of industries.
Absolutely. And maybe, as you, the listener, think about the challenges you might face in keeping your own equipment in top shape.
Yeah.
You know, that ever-present concern about costly downtime.
Yeah.
Just consider the potential impact this kind of technology could have, on your maintenance schedules, your overall operational efficiency. It's definitely a powerful tool to keep in mind when keeping things running smoothly is absolutely paramount.